and lose to Gibbs because we really don't understand it and we just use it for what little tiny purpose we need and ignore the rest. So if you become one of those people, you will come back and give this lecture every year. But it really just tells us if this reaction will work or not before we actually mix the stuff together and waste it. Or we can figure out the temperature range over which it'll work, so we make sure to start with the right conditions in the lab. But other than that, and it's a state function, so the test asks you to give some examples of state functions. Enthalpy and Gibbs are both state functions, independent of path. You don't need to know why for Gibbs, and you can pretty much obviously tell why for enthalpy, but they're both state functions. So when you're looking to calculate entropy, you're going to use the table 13.3. If you're looking to calculate Gibbs, you use 13.4. But essentially, they're the same equations as Hess's law, which is convenient. You only have to really learn the bond energy thing, which is reactants minus products. And then everything else is just like Hess's law. Like the delta H for Hess's law is going to be the sum of the products minus the sum of the reactants. And it's exactly the same for entropy. It'll be sum of the products minus sum of the reactants, but you just use chart 13.3 instead of 13.2. And for Gibbs, you can do the exact same thing, products minus reactants. And the equation is exactly the same. The only other equation you have to learn in this module is for Gibbs. It's always equal to what? Enthalpy minus temperature times entropy. And that can help us figure out what temperature situation we want in the lab to make sure that the reaction actually works, because Gibbs has to be negative or nothing will happen. And there are some things that you can't really get normal conditions to make the reaction work anyway. You'd have to have ridiculous temperatures to make it happen. So, those reactions, if you really need it to run, you need a good lab. We don't have that. So, let's see. That's really it. That's about it. And when we do these practice problems, it will definitely clear up some of the questions. So, let's start with review question 5. And we can start with Micah on that one. It says, which of the following substances have a standard enthalpy of formation of 0?
I think we did that one. We did 1 through 5 for review questions.
Right, we just review it and make it work. It's an easy point on the test.
Basically, it's just O2 gas and then chlorine 2 gas.
Right, because anything that's a homonuclear diatomic in its elemental form is going to be a gas. So hydrogen, and then these 7 have to be homonuclear diatomic, have to be gas to be in their elemental form. And only things in the elemental form give you a standard enthalpy of formation of 0. So if I give you some more options, things might be more similar to what you'll find on the test. Let's see. Which ones of these would have a standard enthalpy of formation of 0?
Directly to me.
Yeah,
Okay. I think magnesium solid would be one.
Yep. You guys have seen the real metal magnesium in its solid form. That's how it exists as an element.
I know H2O liquid, O2 solid cannot. H2O a molecule cannot be equal to 0.
Right, because it's a molecule, not in its
And
elemental
then
form.
O2 is not a solid in its elemental form. Although that'd be pretty interesting.
Well, we'd all be dead, but
Yeah.
if that's how it wants to be naturally at our current temperature and pressure, we're dead. How about mercury liquid?
I think I've only seen mercury as a liquid
Yeah.
metal, so I think it would be considered a 0.
Yeah, mercury in its elemental form is a liquid. Where is he?
It's a blue,
A blue guy.
in the corner.
Yeah,
It's
Tan
like a mix
again.
of pink and blue. It's
There
actually
he is.
pink.
So that's our only metal that exists in liquid form as an element. All the other metals should be solid in their elemental form. I don't think he put such an awful trick on the test, but mercury's a liquid. And gas, all the homonuclear diatomics are gases, including hydrogen. All of the
Noble gases.
noble gases are gases. So column 8's all going to be gas in the elemental form. Everybody else is solid in its elemental form except mercury, that I can think of. So as long as you get the homonuclear diatomics and the noble gases as gases, the homonuclear diatomics as diatomics, mercury is a liquid, everybody else is a solid, then you're safe. And nobody's going to ask you anything about the scary guys down there. So we don't worry about them. Why have I been seated? That wasn't smart. Aaron. Number 6 has 2 energy diagrams, which I hope everybody can currently see on their paper, or on their neighbor's paper. Which of the following diagrams indicates an endothermic reaction?
Diagram 1,
And how could you tell?
because it gained energy from a solid.
Good. All endothermic reactions gain energy from reactants to products. And what do you think the delta H is for it?
It looks about 55
And make sure you put a unit.
kilojoules.
55 kilojoules. So that works. If you said anything between 50 and 60, I would probably mark it right. 55 being what I said, which I don't know if that makes it any righter, but you know. Good. Liam, draw an energy diagram for a reaction with a large activation energy and a delta H of 0. I'd like to see that reaction, but feel free to draw it. Make sure we remember goggles, speaking of activation energy today, when we go outside. Oh, and he's got it. Okay, so his products and his reactants are at the same energy level. On the y-axis, his activation energy bump is big, not small, so that's exactly right. So you just have to pump a ton of energy in there to get right back to the same energy where you started. I guess if you really want the products instead of the reactants, it might be worth it. So, Austin, if you have 2 50-kilogram blocks of copper, which would make you very wealthy at this point, because copper is like high on the thievery list, and one is at a temperature of 50 Celsius, and the other is at a temperature of 25 Celsius, which has more entropy.
The one at 50 degrees Celsius will have the higher entropy because as you increase temperature, disorder increases.
Right, so even though they're both solid, at 25 they'll vibrate less than at 50.
Because the molecules will move around faster.
Right, each molecule will have more energy at a higher temperature, so even though they can't move freely, they can vibrate more vigorously. So if the masses were different, say we had same conditions of temperature for 2 bricks, but we had like 1 copper penny and 10 copper pennies, which one would have more entropy?
The 10 copper pennies.
Mm-hmm. More mass also gives you more entropy, and I think that might be what's on the test, but I don't remember. So higher temperature, more entropy. More mass, more entropy. The more stuff you have, the more chaos you have. And you all know that to be true as well. My house is like a testament to the fact. Get rid of stuff, get rid of chaos. It works. That might be the most important detail of the day. Maybe I'll go home and clean. Number 9 says, when you study, your brain neurons store information and your brain becomes more orderly. Why doesn't that contradict the second law of thermodynamics, Kristen?
I'm not sure this is right, but is it because your body has to burn fuel to blink, and then that increases the heat of your surroundings, so the entropy goes up. And if the entropy increases surroundings, it's going to be the entropy decrease of your brain.
Yes, so you can't tell your mother that you can't study or you'll disorder the world. Also not a successful excuse. Please disorder the world and study hard. It's okay. But yep, that's exactly it. And Grace, if a chemical reaction is exothermic but has a negative entropy, so that means, well, what does a negative entropy mean?
It means it doesn't cause disorder.
Right, it becomes more orderly. So it's exothermic, but it makes something become more orderly. So can we picture this? Something's burning up, but somehow becoming more orderly? I don't know. I don't know about this. What could you do to the temperature to make that reaction actually happen? That seems like an unlikely event to me. So Grace gets the hard problem. So what would you do with this?
Lower the temperature.
Lower the temperature, and why?
Because you're making it have less energy. I'm not sure.
So here, I'll write the equation on the board for Gibbs. So Gibbs is enthalpy minus temperature times entropy. Now what did it say about enthalpy for this?
Negative? No.
Mhm.
Oh, negative.
It's exothermic, right?
Yeah.
So this is going to be a negative number. And then what did it say about entropy?
Negative.
Well, did it?
Yes.
Entropy is negative. Okay, entropy is negative. Okay, so if we had this to be negative and this to be negative, what does Gibbs have to be for the reaction to actually happen? Positive or negative?
Positive. I don't know.
Negative.
Okay, so key definition. Yeah, that's good. Okay, so Gibbs has to be negative, right? Less than 0, right? So Gibbs has to be little, right? So how can I make this? I want to subtract a big negative, right? How to explain? Anyone have a great idea of how to make this clear? Sometimes it works better when...
If t was negative, wouldn't that always be make?
Well, but what does t have to be? Can t ever be negative? Oh, yeah, it's terrible. This is Kelvin. This is one of those times, just like with gas laws, that temperature has to be in Kelvin, because if you look at your chart, you have to cancel out a Kelvin in entropy, because entropy is given in joule per mole degree Kelvin. So, that is our entropy unit. So we're going to have to use Kelvin there. So we can't just give us a negative temperature, make this positive, diminish this, and be all set.
I guess if you have a lower temperature and the temperature's multiplied by entropy, then if you have a lower temperature when it's multiplied by that entropy, then the enthalpy minus the temperature times entropy will give you the negative Gibbs. So
Okay.
as you lower the temperature, it'll lower,
Right,
the
so
product.
if this is negative, and then you subtract a smaller number minus a small negative, right, the more you can diminish this, you need to keep this side negative, right? So the smaller you can get this term, the more likely you are to keep this negative.
Oh, I see. Yeah.
And the temperature is the only thing you can really change.
Exactly, because enthalpy is a state function. Entropy is defined in this case as increasing or decreasing, which, right? So you have to run this at a really cold temperature. And there's another problem that we'll look at for this. But yeah, So that, I know that's tricky, but you really need to think through each definition. Gibbs has to be negative. Enthalpy has to be negative. Disorder is decreasing, so entropy is negative. What can I do to temperature to give me the best chance of getting a negative Gibbs? I decrease it, so I don't end up making that delta S times T term so much that H. I don't even know if I would want to make that an inequality. That might be why it's confusing. Even if I say this is equal, right, I want to end up with something negative. So I don't want to subtract a big negative there. If I beat this dead horse, I'll probably become confusing. Okay. That'll be the hardest question on the test, and it's very similar to practice problem 8. So that is kind of where we should spend our time. And it's pretty easy to tell when you're wrong. So at least there's that. But until we get there, which practice problem should we start on? 4, 5. 5?
Yeah.
Okay, Jenny, can you find it? Practice problem 5 says, suppose you synthesize ammonia with the following reaction. So you take nitrogen dioxide gas, you react it with hydrogen gas, you produce ammonia gas and water gas. So, completely off topic, what would be the entropy in this situation? Would entropy be positive or negative?
Oh, that's me.
So what has more entropy, a solid, a liquid, or a gas?
Gas.
Gas. Do you have anything that's not a gas here?
No.
So if every single reactant and every single product is a gas, how do we tell if entropy increased or decreased?
You count the moles.
Count the moles. So if you have how many moles of reactant gas?
9.
9. And how many moles of product gas?
6.
So if you go from 9 moles of gas to 6 moles of gas, did entropy increase or decrease?
It decreased.
I didn't hear you.
It decreased.
Entropy decreased. So, good. Entropy decreased. That's nice. But that's not what we're worried about. We need to find energy. So go ahead and put that on the board. That one is too long to talk about, I think. I should have talked about that with everyone else, but making you put that on the board. While she puts that up, well, we can talk about the same sort of thing with Jolene for number 6 while Jenny puts up number 5. Then we won't waste time. So
it's positive, negative, negative.
Okay, positive, negative, and
Negative.
and how do you know? So let's look at A. We go from reactants that are aqueous and aqueous to products that are aqueous, liquid, and gas. So how do you know entropy is positive there?
Increase. No. Yeah, it increased. The reactant, sorry.
Tell me real loud, my ears aren't working today.
It increased like the moles from the reactant.
Moles of what? What is the only thing you care about if it's available?
The highest. Like the gas.
Gas.
Yeah.
Gas is the only thing you care about when it comes to entropy. If you go from reactants with no gases to a product with any gas, entropy is increased, guaranteed. Because gas has so much more chaos than a liquid or a solid that it just is a huge difference in entropy. So because there are no gaseous reactants and one gaseous product there, definitely entropy is increased.
So if it was like the reactants were like aqueous, and then like gas, solid, it would still be positive because there's just one.
If you make a gas entropy increase, that's a rule, at least for you guys. I'm sure we could contrive some way to get around that rule, but that's going to work for you guys every time. You produce a gas and entropy increases. You have a gas in the reactants and not in the products, entropy decreases. Can I see it? It looks like 2.06 moles. Well, then put that. Do you want a different marker? That's not a good marker. So B says you have two gases, you produce a solid and a liquid.
That's negative because of decrease.
So entropy decreased. And C, you have all gaseous products and reactants, so how do you figure out that entropy was negative?
That's low.
Tell me
I'm
that.
not sure.
Okay, so for that one, it's just like the one I asked Jenny from number 5. How many moles of gas are there total in the reactants? So you have 1 mole plus 3 moles in the reactants. So how many total moles for reactants? 4. And how about the products? 2. So if you go from 4 moles of gas to 2 moles of gas, you have much less chaos. It's like going from 4 moles of children to 2 moles of children. There's much less chaos. Not that there's a mole of children even ever in all of history added up. But a mole of popcorn would kill us all, so. The next one involves math 2. So, Saul, do you have 7?
Yeah, that would be negative.
I don't even know what the question is yet. Hold on. Oh, there we go. No. It is negative. Oh, but you literally have to calculate the numerical delta S. Jenny did that too. She's like, oh, it's negative, and I'm like, oh, it's a number. So, and here's how you know on the test. I actually had to think about this when she didn't do it, because I'm like, well, how would they know on the test? Teaching your own kid is eye-opening. If it asks delta S, like in number 6, it does this. If it asks for this, or is it down there? Where's it? Right there. If it asks for the standard enthalpy with this little tiny degree mark, you have to calculate a number. If it just has delta S with no little degree mark, you just, So we'll chug through that one together, Saul, don't worry. Let's look at what Jenny's done here for number, what is that, 5? All right, so how much energy is released when you form ammonia? She didn't put up the equation, but you have it on your paper. So we take ammonia, it gives us 35 grams of ammonia, and she converted to moles of ammonia, and she put an H3 there. So then, take the moles of ammonia, and you look at your chart. Do you have that on the chart? So NH3 gas, is this enthalpy? Or enthalpy, what are we doing? Energy, so enthalpy.
I think I did something wrong.
I don't think you did anything wrong. I think I can't think. Oh, I think I'm looking at number 6. That would be a problem. Here we go. All right, so I'm just going to write the equation so I can stop being confused. Okay, so we've got a reaction here. She found moles of NH3. So we look here. Then we take, is that a multiplying mark?
No, that's a minus sign.
A minus sign?
Yes.
Then there's some sort of little problem here. So
Probably.
we've got Hess's law, which says this. The sum of all the products minus the sum of all the reactants. No, I don't want a sum mark, I want a parentheses. Okay, so products. We've got ammonia as a product, so that should be 2. Oh, I know what you're doing here. So you should have 2 moles of ammonia times the enthalpy for ammonia which is negative 45.9 on the chart. And then kilojoules per mole. Right, and then the other product,
I think I didn't use the chart for this, and I
Yes,
think
you
I tried to do
did.
something else. So.
you had to because you have a kilojoule here.
Oh.
So water is a gas, so you have to look up water, gas, and that's negative 242. And here's what I suspect you did. Where's my calculator? I'm guessing that negative 242 times 4 moles, well, this would be a plus sign, 4 moles times negative 242 kilojoule per mole. That's water's standard enthalpy. Where's my calculator? It'll be faster to find it. I think things are. Alright, so if I do 242 times 4, no, you get something different. So for that, I would get 986.
You gotta do the reactants, like subtract reactants, right?
Yes. Oh wait, moles cancel because of this. So then here, 45.9 times 2. So that'd be 91.8 kilojoules because the moles cancel. So that's negative. Alright, so these two are the products. Then we subtract out the reactants. And that would be hydrogen gas. Hydrogen gas is 0 because it's an element. So, and then nitrogen dioxide gas. So look at the chart, nitrogen dioxide gas is 33.2 kilojoules per mole, and how many moles is that? 2. And 2 moles. Alright. So, I do 33.2 times 2. Then we have to think significantly. So that is 66.4 kilojoules. Okay. So, then, is that a negative or a positive? Positive. Okay. I'm going to put a little plus sign there just so I keep track of that. So I've got negative 91.8 plus a negative, so I'm just going to minus 986. And then I get 1077.8. But this has a tens place and this doesn't. So I have to round to the ones place. So 1078 kilojoules here, which is negative, so it doesn't make the point. Minus 66.4. And of course here I'll also end up rounding out that tenths place. I get negative 1144 kilojoules. And that's not even the end, I bet.
I didn't round at each step if the significant figures.
Yeah, I didn't either.
Okay.
So some of my
Here's-
answers
I
are
got
wrong.
positive.
That's fine, that's not gonna get you much off. I usually ignore significant figures the first time you make a mistake on a test, and the second time I took off an even point. But, okay, here's the kind of key point of knowing when to round. Don't round when you're multiplying and dividing till you get all the way to the end. When you're adding and subtracting, you really do have to basically round